Hello, everyone. Let's start today's class. A little bit of recap of what we have learned so far. We talked about some very primitive data types. Then we moved on to some compound data types. We looked at some algorithms, and then we talked about some the concept of functions and abstraction, decomposition. And we also looked at using classes as a method to do some abstraction, data hiding, and decomposition in our implementations. What we want to study today is a completely different topic, and this is related to the efficiency of the programs or algorithms that we write. What we are interested in is measuring the time required for an algorithm to do something, and what we would be really interested in is measuring the order of growth of algorithms based on the size of the input that they receive as part of its execution. Um, the notation that we use is the Greek letter Omicron called big O, and we will take a look at various complexity classes. And as we go along further into this lecture, you would be able to know what are the different complexity classes for various algorithms and how it depends on how we write the algorithms. Why do we need to measure this complexity for algorithms and how it is used in computer science or when we write programs? What we want to do is have a way to predict how the algorithm will behave provided a certain kind of input, and whether the size of the input or the type of the input has any bearing on how efficient the algorithm is and how long an algorithm takes to run based on the size and nature of the input. And what are the different choices that we can make while implementing the algorithm that will result in changing its complexity, even if at all possible. In some case, in many cases, it's not even possible, but we will take a look at that. And what we are trying to find out is the limits around the time efficiency or the efficiency of running of an algorithm. Are there any fundamental limits on that? Are there any bounds on top and bottom of it so that we can identify how long it will take when the input size grows abnormally large to millions or hundreds of millions? And why do we worry about that? We can say computers are very fast nowadays. Back when they were originally invented, they would take up a whole room, and people would use punch cards to program, and something that used to take 5 to 10 minutes of calculation time at that in those days can be done in fraction of a second on your phones today. So why do we need to worry about the efficiency of programs that we write? And the reason for that is that as computers are becoming faster, the amount of data that they have to deal with is also growing abnormally large. For example, in last year, Google served about 130 trillion pages in searches. That's the amount of web pages that it has to go through when providing results to any user for a particular search. And data actually was 400,000 terabytes or 400 million gigabytes of data that they have to search. And if they simply use a brute force algorithm, which is going through all the pages one by one and trying to find something, that simply would not work. That's why it's important to write efficient programs and efficient algorithms. And when we talk about efficiency, there is a concept of time efficiency and space efficiency. We can write very efficient algorithms that take up a lot of memory, but that's always not always possible. So we have to find a way to measure the efficiency of a program which is independent of time and space, and is dependent on the size of the input that they receive. We can always try to make our algorithms more efficient. For example, you would remember from our lecture of recursion and dictionaries that when we try to find out the Fibonacci of just a small number, 34, for example, the number of operations that it had to do was about 11 million. But when we implemented a smart solution by storing all the pre-calculated or storing the calculated results in a dictionary so that it does not have to recalculate them, the number of operations came down from 11 million down to 65. So that's how we can make our programs efficient by writing smart algorithms, but that's not always possible. And we have to look at the efficiency of a program for the worst case scenarios. Now, when we look at computational problems, there are many challenges, and any program can be implemented or written in many different ways. Um, but for many given problems, there are only a few ways in which you can implement it. You may be able to use an iterative solution as opposed to a recursive solution, but the underlying principle of solving any particular computational problem is limits you from your options, and you can implement only up to a certain amount of efficiency, and beyond that you cannot go. Once you start programming some complex algorithms, you would identify that limitation. So there are many different ways to compute the efficiency of a program that we write. We can simply be a little bit scientific. We can use a timer when before calling a function or before calling an algorithm, and then use the timer of the computer to to get the time of when it finishes running, and just see what the difference is. Secondly, we can count the operations, and we know how much time it takes for those simple plus, minus, multiplication, equality check, or those kind of simple operations. How much time a computer takes to do them. We can count those operations and simply represent an equation that represents the efficiency or complexity of our program. But what we are interested in is a little bit more abstract method, and that represents the order of growth of the efficiency of an algorithm depending on the size of the input. And we will take a look at many different examples, and that way it would become evident that this is the most dependable or most usable method of identifying the complexity of an algorithm. Now, this is the first example of using a timer to see how much time a program takes. We can start the clock before doing something, then do something, check the timer again, and then print how much time it took. Now, this simple function of converting Fahrenheit to centigrade, Celsius, or other way around, takes in a number, does some calculation, and gives us the answer. Now, the number of calculations or operations, we can simply count it here. There is an addition going on here. There is a division in the formula, and there is one multiplication. So it takes 3 operations to do this simple step. And the only variable being used is an integer itself. So by increasing that 2 million, 100 million, or 1 billion probably would not make that much of a difference. Now, our goal is to evaluate different algorithms, not just simple ones that do operation on a number. The running time can vary between algorithms. So if you look at this simple example, the running time varies between algorithms. If it was a slightly different algorithm, it would take different time. And if we write it a little bit differently, the time varies, and that would be a problem for us. And simply an efficient or a better computer can compute this in lesser time than an older slow computer. So that's also a problem. This method of using the timer to calculate the efficiency of a program does not work very in a very dependable way. And time is not predictable because the input here was just an integer, whereas when we talk about complex algorithms, they depend on large lists or other kinds of inputs that make the calculation very hard. So time is different when we provided different inputs, but we are still not really creating a relationship between input and time here because it depends on a number of other factors like the fastness of the computer or different way of doing the implementation. Um, let's take a look at another example. For example, we can instead of using a timer, we can count the number of operations, and that way we can probably come up with an equation that is represented based on the input that we have used. So here, as I said earlier, the Celsius to Fahrenheit conversion simply uses three operations. It's not a complex algorithm, and its time complexity is constant. No matter what the size of this number is, it would only do three operations every time. Whereas here, if we are trying to find the sum of all the numbers from 0 up to x, we have to do a little bit more number of operations. So we are setting the total to 0. That's one operation. Then we are setting I to start at 0 and go all the way to up. For every time we go through this for loop, that's one operation. And then this total increment by the amount of I is two operations. Basically, we are saying that total is equal to total plus I. So total plus I is one operation, and then this equality back into total is another operation. So that's two. So if we count the total number of operations here, and we are doing all of this X number of times, all of these operations, this one and these two operations, they will be done X number of times. So if we create a simple mathematical notation for that, it's 1 plus 3x operations for this algorithm. One operation here and these three operations here executed X times. So this represents the complexity of the operation, and we can know that when X grows abnormally large, this one wouldn't matter at all, and our complexity for this would be directly proportional to whatever the number X is. So this represents a linear complexity. We will take a look at other classes of complexity in a bit. So this kind of calculation of counting the numbers, it depends on algorithm. In that scenario, yes, we are okay. Different types of implementations would cause a problem for us. It is independent of computers because we are representing the whole operation using a mathematical equation that depends on the size or the amount of input. So that way we are covered. But there is no clear definition of which operations to count, and different programming languages perform different operations in many different ways. So which operations to count, whether to count them as one or two operations, we don't know. There is no clear definition of that. So in a way, count varies for different inputs. Yeah, we can come up with a relationship between input and the count, which we did in terms of that equation. So that way we are covered. But still, we need a better way to cover all of our bases or all of our questions here. And for that purpose, why we want to do that is to evaluate the algorithm and not the machine. We want to evaluate the scalability of the algorithm, and so that if the input becomes abnormally large, is our representation of that complexity in terms of that equation still holds or no. And this kind of representation that we want to do is dependent on the input size, the nature of the input and the size of the input that we provide to that algorithm, and that's what we will study today. What we are trying to do is get an idea by looking at an algorithm or by analyzing it. We want to find out how complex the running time would be, and we can do that in many different ways. We will take a look at a few examples as well. But we want to represent that complexity in a way that is dependent on the size of the input to that function or that problem. And the what we need to do is that depending on the algorithm, the way it is written, the number of steps that it has, we want to get an idea by using some mathematical representation of that algorithm to see what are the different cases that will happen when we run the program. Maybe there is a best case scenario, maybe there is an average case and and a worst case. As I said in the beginning, that we want to put an upper bound on the execution of the algorithm. So in a way, we are always trying to calculate the worst case scenario, which represents the actual complexity of the algorithm. Uh, so we want to express our algorithm efficiency based on the size of the input. This earlier example, for example, where we said that we would sum all the numbers from 0 to x, where x is an integer. It's a linear complexity. All the statements would run x number of times within a loop. But then the input of the list could be a list as well. So that way, depending on what's going on inside, we would be using a whole length of the list for those operations. So maybe it would increase from linear to let's say quadratic. Um, and there are many scenarios where the input is more than one. So we have this function, as the name specifies, is trying to search for an element within a list. So we are trying to find E in the list L. So whatever kind of implementation we do, we have to go through the whole list to find whether E is present in that or not. And there are many different scenarios. Maybe E is the first element. Maybe E is somewhere in the middle of the list. Maybe it is not even present in the list. So in the worst case scenario, we have to go through the whole list length of L to find whether E is present or not. So in this scenario, whatever E is does not matter. The algorithm that we would write for this scenario would depend on the length of L. So when there are more than one parameters to a function or an algorithm or a problem, we have to identify which one is actually causing the or on which input is the complexity actually dependent upon. So here's that example that I mentioned earlier. We have a list L, we have an element E, and we want to find whether E is present in L or not. The implementation is very simple. We will take every element in L and we will check whether it's equal to E. If it is, as soon as we find that element, we will return true. Otherwise, if we go out of this for loop and still have not executed this return true, which means this statement has not become true at any time all the way through to the end of L, then we would be returning false. So here, when E is the first element in the list, that is our best case scenario. This return true statement would be executed the very first time we come into the for loop. But when E is not in the list, that's the worst case scenario for the running of this algorithm. And that would mean that we have to run this loop the length of L times. So that would represent the upper bound or the worst case for our algorithm. An average case is when E was somewhere in the middle of the list, so that we search through halfway, and this is where we found E, and we return true here. So that would represent the average case. But we want to measure the complexity in a general way. We cannot assume whether the list is sorted or not, whether E is present or not. We want to identify a mathematical equation or a representation in terms of the size of the input, whether how much time this algorithm would take. And for that purpose, we know that, let's say, for the worst case scenario, when E is not present in L at all, it would have to run the length of L times, and that would be the upper bound on the complexity of this algorithm, which means that the complexity is linear and is proportional to the length, or is exactly equal to the length of the list for searching for the element. Because if it's not there, we must search the entire list and go to the end of the list for completing our algorithm. And this is the case that we will actually focus on when looking at any algorithm. What is the upper bound or the worst case scenario, or on the number of operations that an algorithm has to do? And why do we do that? We do that because input is usually, for complex algorithms or real world problems, the input is usually very big. And we want to identify the growth of the program's runtime based on what the input was. As I mentioned earlier, we want to identify the upper bound on that growth, which represents the worst case scenario on any kind of algorithm. And we don't have to be very precise because when it comes to complexity classes, there are just a few of those that we can put any algorithm in. We just looked at a constant algorithm for converting a number from Celsius to Fahrenheit. We looked at a linear example of searching for an element E in a list. What we are trying to find out is in which order or complexity class this falls in. We don't have to count the exact number of steps based on the amount of input or the nature of input, but we want to identify an order of growth for an algorithm based on the input size. And for that purpose, we will have to take a look at the largest factors when it comes to counting the number of operations within any algorithm, and those will provide us an upper bound on the growth of the function, depending on the size of the input in worst case scenarios. Now, this big O notation, or Omicron Greek letter, as I mentioned earlier, this one here is what we use to identify the complexity class of an algorithm. And this, what it describes is the worst case scenario, worst case running time of an algorithm. And we will take take a look at few examples of how this is calculated. And we do that because this is the bottleneck. The worst case is always the bottleneck within any algorithm. And we, for surety, we can never be sure about whether it will always run to the average case or the best case. And when measuring the complexity of algorithms, we always look at this worst case. Now, this big O notation, or the order of growth that we will identify for the algorithm, is the rate of growth depending on the input size of that algorithm. And the reason for that is that we are evaluating the algorithm and not the fastness of the machine or the nature of the implementation. Although we are looking at the implementation, but whatever the implementation is, based on that, we are trying to evaluate that algorithm using this notation. Now, coming back to the factorial calculation with an iterative implementation, we have done that in one of our previous classes. So there are a few operations here, and if we try to find them or identify them, we are going to have take a look at each line of this algorithm. Uh, so the input to that is a number n, and within that we have a loop here. And within the loop, we are doing an operation answer times equal to n, which is answer is equal to answer times n. So we have two operations here, the multiplication and the assignment. Then we have n minus equal to 1, which is another two operations. We are um, assigning n minus 1 to a temp variable and then assigning that temp variable back to n. If we try to calculate the number of steps within this by using this assignment, for example, then returning the answer as well, we come up with this simple mathematical expression 1 plus 5n plus 1. Um, so there is a check here, two statements here, two statements here. So within this loop that runs n times, we have 5n operations. We have one return after it and one assignment before it. So this is the other one and one here. Now, when we try to find the complexity, we can see that when n grows abnormally large, if that's in hundred thousands or millions, these ones won't matter at all. These are constants, and whenever we are looking at this kind of expression for the complexity of an algorithm, we never worry about the constants. And we also don't have to worry about the multiplicative constants in front of the variable that we are trying to gauge the complexity of the algorithm on. So the complexity of this algorithm is simply this n here within this whole expression. The only significant item that we have to worry about is this number that came in as the input to this algorithm. And the complexity is linear. It is directly proportional to the number n. Whatever the number n is, the number of operations or the time being taken by this factorial calculation is directly dependent on that. So we will ignore the additive constants and the multiplicative constants within the expression once we have calculated the number of steps here. So what does this big O of n measure? This basically is what we are interested in is describing how the algorithm will behave as the size of the input grows. So we want to find a relationship between the complexity or the expression that we have identified for those number of steps, and relate that back to the size of the input that we provided. So when that size of the input gets very large, how does that affect the running time of the algorithm? That's what we are actually interested in knowing. And for that purpose, the only significant item in this whole expression, when n becomes abnormally large and goes into millions or hundreds of millions, that is the only part of this expression that we are interested in. There are many other different types of complexity classes mentioned here. And here are a few examples of, let's say we have gone through the algorithm and we have calculated what it is doing inside. So if an expression, if an algorithm is represented by this expression that says n square plus 2n plus 2, within this we are only looking at, we only have to look at the dominant term, which in this case is n square. When n becomes abnormally large or large enough, this 2n wouldn't even matter in front of it. And this 2 is just a small number. We don't even have to mention it here. So the complexity of this whole algorithm is basically n squared. So we are looking at the dominant term within the overall expression, and that would be the complexity of the algorithm. And this expression we came up with is by looking at the algorithm and analyzing it step by step of what kind of operations it is doing, whether it has one loop, two loops, whether those two loops are after each other, or whether one of them is inside the other loop. So that would represent that would drive how we create this expression representing the complexity of the algorithm. Uh, so let's take a look at another example. Here we have a very large constant, another very large multiplicative constant in front of n, but the dominant term here is still n squared. The only thing I can say about this algorithm is this is a very inefficient algorithm. I don't know what it's doing here. It doesn't even make sense to do something 100,000 times every time. But still, when n goes into millions or hundreds of millions, these two terms would basically disappear in front of it. And the only thing that would matter is this n square. Um, I will show you a few examples in a minute, and you would be able to identify why these terms won't even matter when n becomes very large. In this example, we have n being involved in two different types of operations here. We have log of n and n by itself and a constant 4. The dominant term here again is only n, so the complexity of this expression would be big O of n. And over here, the dominant term is n times log n, so this is log linear algorithm. And in here, it may look a little bit difficult to identify, but between n raised to the power 30 and 3 raised to the power n, this is the dominant term when n becomes very large. So here's a simple graphical explanation. You can see that the bottom axis is the size of the input, and the y-axis here is the number of operations that it would have to execute. And you can see that constant is somewhere right here. It's just increasing directly proportional to the just the amount of input or the size of input. Then we have some a linear implementation here that is increasing very nicely, but in a very constant manner. This would be a quadratic complexity algorithm. Logarithmic algorithm is actually even more efficient than linear. It is somewhere down here again. And then we have a log linear expression, better than quadratic, but little bit takes a little bit more time than linear. And exponential, if we extend this graph a bit, this increases very rapidly, and would be one of the very complex or time-consuming algorithms. One example that we took a look at in our previous session was solving the Towers of Hanoi problem, which was an exponential problem. Now, when we have a combination of statements within the analysis of an algorithm, there are a few laws that we use for solving them or simplifying them. One of them is the law of addition. So if there are two functions, um, and they are one after the other in terms of the implementation of our algorithm. So if there is a complexity of function n which is being added to the complexity of function g, and both depend on the same input of n, then the law states that the overall complexity would be the addition of the time required for function f and the time required by function g. Here, for example, we have a loop that prints a n times, and then right after that we have another loop that prints b n times n times, so n square times. Now, overall, the complexity of the first loop is linear. It is dependent on just the number n, whereas the complexity of the second for loop is n squared. And when we add them up, it is big O of n plus big O of n squared. Here, this is the dominant term, and this becomes insignificant when n is very large. So our complexity for this overall 4 lines of code is big O of n squared, because n squared is the dominant out of n and n squared. Uh, Here is another example. So we have a function that has two for loops. One of them is nested inside the other one. So now this inner for loop would run n times, whereas the outer for loop would also run n times, but for each of those executions, this for loop will run another n times. So the complexity for this would become big O of n for the outer times the big O, or the complexity of the overall loop being run twice. So that this nested for loop also produces the complexity of the quadratic complexity or complexity of n squared. So these are all the classes of algorithms. Every algorithm that you can write falls probably in one of these. So this is constant running time, log running time, linear running time, log linear running time, and this is polynomial efficiency. The only problem that we saw was two nested for loops, and that was n squared. So any constant raised to the power n is polynomial complexity. And this last class is the class of some few algorithms which grow exponentially in size. For example, towers of Hanoi and Fibonacci, as I mentioned earlier. Um, for number 34, for example, if we have a simple implementation of Fibonacci that was doing 11 million plus operations. We will take a look at a few of these in this session, and the rest we will take a look at in the next session. So these graphs I have shown you before as well, and that shows if you look at the y-axis, the number of operations that it mentions grow quite a bit for every next class of algorithm. As when we get to exponential, they are in 6 raised to the power 11, for example, by only reaching n to the size of 51. So this is increasing quite abnormally large as compared to something which is log linear. At 51, we are only somewhere about 300 over here. So this table basically puts everything in perspective. For a linear complexity function, the size of the input doesn't matter. For n is equal to 100, it takes the same amount of time when n is equal to 1 million. Log n is still fairly good quality of implementation for our algorithms. At 1 million, it is only running 6 times here. A linear complexity function would increase by the same rate with which the input is being increased. Log linear is also one of the few complexity classes which is considered efficient. When the input size is close to 1 million, it's running only 6 million times, which is not bad. N squared kind of implementation or algorithms do tend to get very large or take a lot of time for a size of 1 million input. For example, it's running quite a bit of times. But when it comes to exponential complexity of algorithms, you can see how the size or the complexity increases with the size of the input. For 1000, when n is only 1000, even for a quadratic function, it wasn't bad. It was running a million times. But for an exponential function, you can see how large this number is. And you cannot even, although Python will calculate for you, but it would take pages and pages to print out this number when the input is close to 1 million. And when we talk about actual real world scenarios, we are talking about hundreds of millions as the size of input. So let's take a look at a few examples of different complexity classes. Linear complexity is the class of algorithms that usually have a single loop, and we have one simple iteration of that loop. For example, here we are doing a linear search of element E within list L, and we are simply going through the list one time. And when we find it, we set a variable which we return at the end. So the complexity for this implementation would be, if we try to calculate the terms, that would be 1 plus 4 and plus 1. We know the constant doesn't matter, the multiplicative constant doesn't matter. This n would be the actual complexity of this algorithm here. So searching within an unsorted list for an element E, the complexity would depend on the size of length, the size of the list L, or the length of the list L. So this is a big O of n, where n is the length of this list. Uh, this is a simple representation of how things are stored in the memory. For example, we want to identify whether we are taking a fixed amount of time when we are accessing an element within a list. If the list is all integers, we know one integer takes 4 bytes to store. 1 byte is 8 bits. So if we know we have to go to the ith element, we just multiply this by 4 bytes or 32 bits. We know which element we are going to get at. But in many cases, when we are dealing with lists can have any kind of element within them. List can also have a list. A list can have a Boolean value, for example, which is represented by just 1 bit, but it could have an integer value or a smaller list in it. The way it is represented is that we still have a list of pointers which still take a very fixed amount of space in the memory. So if we know which element it is, at which position it is, we can simply multiply that with the number of bytes that it takes to store this memory. We can get to that place and then get the element at that which is being pointed to by that element or by that pointer. So accessing elements within a list still takes constant amount of time. That was just one extra bit of information that so that we don't have to worry about how much time is being taken for us to get to the ith element for L, for example. That's constant time. We don't have to worry about that. What we have to measure here is this equality operator or this return statement, checking whether it's greater or not, counting this return statement. So if we are searching through a sorted list, uh, and we get to a point where the element that we are looking at becomes if it is equal, we return, but if it is less than that, then we stop searching. That would mean that we have a descending order list of integers. We are looking for an element E. We start looking one by one for each element. And at some point, we would become sure that E, if it was there, it would have been before this point. It cannot be after this point because the list is already sorted. So can we say this kind of implementation is better than linear search? We cannot say that because we have to consider whether E is completely absent from this list. That would represent our worst case scenario. And in that case, we would still have to go all the way to the end of the list to identify whether E is present or not. And for that reason, this implementation, whether the list is sorted or unsorted over here, the complexity of this would still be linear. Uh, Another example, very quickly, I will explain this. We have a string that has a number of digits in it, and we want to convert each one of them to an integer, do a sum, and return it. So here we have a few statements, but we can identify very easily now that we have gone through many examples that it contains a for loop that is running the length of s times. So whatever the size of S in terms of its number of digits inside it is, with that would be the complexity of this algorithm. And we can simply say that by looking that this has one for loop that is running S times. or the length of S times. Another example here, iterative calculation of factorial. We have we have a number n for which we want to calculate the factorial. We have only one for loop, which is doing a certain number of operations inside. And this for loop runs from 1 to n plus 1. So it's running n times. So without going into any kind of complicated calculation, we can simply identify by looking at it, now that we have gone through many examples, that the complexity of iterative calculation of a factorial is linear, and it's based on the number itself. Next class of complexity is represented by nested loops. Nested loops mean that we have a for loop here, and inside the for loop we have another for loop that runs a certain number of times, and both of them are dependent on the input that we have provided to this function. So this kind of implementation, when we can identify it very easily. We have a for loop here, and inside we have another for loop, and both of them are running for the size of these inputs. The first one is dependent on L1, the second one is dependent on L2. No matter what we do, the complexity of this would be the size of L1 times the size of L2. So the with that multiplicative rule that we looked at earlier, we can identify that this is quadratic complexity in terms of running time of this algorithm, because it has one for loop, and within that we have another for loop. There may be cases when there is another for loop, there are more than two. We know we have one here, we have another nested for loop inside, but we have one outside as well, which is running in a different number of times based on the input that was calculated within the previous for loop. But if you remember, we have the additive law here. The complexity of this portion of the program is n squared. The complexity of the remaining portion of the program is n, but n squared plus n. If this is the expression that represents the complexity of the algorithm, we don't have to worry about this because this is the dominant term. So the complexity for this kind of implementation, which is calculating the intersection of two sets, whether one is present in the other or not, then that would still be quadratic complexity. Another example for quadratic complexity or nested loop is calculating the square for this number n. All we are doing is running this for loop n times, and then running another loop again n times, and just adding one back into the answer. It's a very inefficient implementation of calculating the square of a number, but the complexity of this is a nested loop within a loop, both running n times. So the complexity for this, we can easily see it's n squared, this n times this n. So we will end this lecture here. We have seen some examples of loops and nested loops, and how to identify what the complexity of that algorithm would be, whether it has one loop or a nested loop, which are both dependent on the input to the function. And we have, if there is a single loop, that usually most of the time it represents linear complexity. And if there is a nested loop, that represents quadratic complexity. So in the next class, we will take a look at the rest of the complexity classes from the previous slide that I showed you. Some very interesting algorithms that fall in those linear log or log and the exponential complexity classes. So we will study those in the next lecture. That would be all for today. We will continue in the next class. Thank you very much.